Hello, everyone. We're going to continue with chapter 3. Chapter 3 is about processes. And as I mentioned before, a process is a program in execution. Okay, so we're going to be talking about process concepts, so what a process is and how it's created and so on. Process scheduling, operations on processes, inter-process communication, so how they communicate together. Okay, the IPC in shared memory, we'll see what that is, and in message passing, the two different models of process communications. We're going to be having examples of IPC systems and communication in client server. Okay, so an operating system executes a variety of programs that run as a process. Okay, what is a process? A process, as I mentioned, is a program in execution. So, having said that, we can say that every process is a program, but not every program is a process. Why is this? Because a process is a special case of a program. All right, a process inherits or extends the program as a parent. So the process execution must progress in sequential fashion. Okay, no parallel execution of instructions of a single process, right? And because that was not really something that is very appealing, multi-threading appeared, which we will be dealing with in chapter 4. So what is a process? A process is a program in execution. The process execution must progress sequentially, okay, and no parallel execution of instructions, all right, of a single process. Now, if you look at the process structure, you can say that the process has the program code. Of course, it's inside the process. It's also called text section, lines of code. The current activity that is happening on the process. This includes the program counter, the processor registers, okay? This means that we have some kind of data structure that holds those and more, of course. This data structure, we call it a process control block, PCB. PCB. It has the current program counter, it has the registers, it has the stack, it has many information that you will see later. And we can always see a process to be a PCB plus a program. So you can see, this program is the body, the PCB is the kind of the soul that makes the process alive. So the process would be a PCB plus program. All right. We also, of course, have the stack, the data section, the heap. Those kind of stuff are also, included in the process. So you have the stack of the process that contains the temporary data, all right? And by the way, the stack, we store in it everything that has been statically allocated, okay? So you store init function parameters, local variables. You have the data section that contains global variables, and you have the heap, okay, that contains memory dynamic allocation. Okay, and that's the difference really between the stack and the heap. Okay, in the heap, you store everything that is dynamically allocated. So in other words, if the process has something like this, int x of 100, okay, so this array has been statically allocated. It's stored inside the stack. Whereas when you say int star x equals int star malloc, okay, 100 multiplied by size of int, that's really a dynamic allocation. So x here is stored inside the heap. Okay. All right. Now, as I mentioned before, a program is nothing but a passive entity. It's code, lines of code. Okay. It could be stored in the disk as an executable file. Now, the program becomes process when an executable file is loaded into memory. That's when it becomes alive and ready to run, right? Okay, and that's when the PCB is added to the program to build the process. Execution of programs started via something like GUI, mouse click, whatever. That's something like Windows, command line, any method that you would call the program, of course. In the end of the day, when you call the program, the operating system is going to be loading this program into memory. How this is done, you will see it in chapter 9 and 10. Okay, and that's when the program becomes a process. If the program is big, it can be actually divided into several processes. So one program is one or more processes. Okay, and now also you can run the program several times for several users. As an example, this means that every user will have their own copy of the process that that loads the program. So imagine that we are loading the Word for multiple users. I have my own document, you have your own document, and so on. So every one of us has their own process of the Word program. Okay. So this is how the process looks like. This is, of course, nothing close to being accurate, but anyhow, here it is. So you have the text, which is the code. That's the code. You have the data, you have the heap, you have the stack, this is, as I mentioned, is nothing close to being very accurate, okay? Now, if we have this memory, it starts from the low index of the memory, and here is the high index of the memory. This is the process. So the process, as you can see, has limits, higher limit of memory and lower limit of memory. And inside that, you have everything that belongs to the process. So if you have a program like this, as you can see, okay, so of course the code, this whole code is stored here in the text part, but then variables, those kind of variables, okay, will be stored in the memory, in the process container. So as an example, you can see something like initialized data in here, uninitialized data are there. Those variables, are in the stack. As soon as you create certain dynamic allocation, it goes to the heap. Here it is. See, here is the dynamic allocation. So it goes directly to the heap. And so on. So this is how the process actually gets loaded, or the program gets converted into a process. Now, this entity becomes alive, and the program counter points to the beginning of the code, and starts executing line by line, and whenever something executes, this kind of data gets updated accordingly if needed, of course. The process has a life cycle. I told you before, the process is an active entity, it's alive, and since it's alive, it has a life cycle. And this life cycle starts from being a new process and ending with, termination, dying. All right. So this is the beginning of the process life cycle, and this is the end of the process life cycle. Inside it, we have a few states. All right. They don't go with this sequence. I will explain it in details now. What is a new state? This is a state. What is the new state? It's the process when the process gets created. So the process is new. When is the process would be in the running state? When you have the program counter pointing at its code, and each and every line gets executed, the PC gets advanced, the data gets updated, so the running state. We have something called ready, we have something called waiting. I'll explain that in details in the next slide. So here it is. This is the diagram of the process state. Here are our 5 states: new, ready, running. If needed, I might be waiting. And we have the termination. Those numbers, they do not represent the sequence of execution, because when you are running, you might go for waiting and then ready and then running and then waiting and then ready and so on and so forth. So they don't have to represent the sequence of execution. All right. So let's say I have a process P1. That represents certain program, and it just got created. So now it's in the new state. When the process gets admitted to the system, so uploaded into memory, it becomes ready to execute. So now the state is ready. So the process now is ready. The process keeps being ready as long it's not picked up yet by the scheduler for it to run. So it's not being picked up yet. It's still in the ready state. As soon as the process gets selected, because you have many processes, this applies to a number of processes. One process now gets selected, so it moves from the running state from the ready state to the running state. So now P1 is running. If P1 finishes without being interrupted, and P1 did not call for any I/O, so it's not waiting for any I/O that come from the disk, and the P1 finished, then it exits the system, and it's now in the terminated state. Okay, the process dies. However, P1 might be interrupted. Why would P1 or any process get interrupted? I explained that in chapter 1. When the process gets its quantum, let's say 2 seconds of executions. Of course, 2 seconds is too much. This is just an example, okay? The 2 seconds of executions, and then the counter is 0. The timer is 0 now. Okay, if you don't know about timer, please go back to chapter 1. So the timer is 0 now, and an interrupt is being generated for the process to be changed. So in this case, P1 will go back to be ready, and P2 will get running. So assume that we have here P1 is now ready, and now P2 is running. Okay. When P2 is running, P2 calls for an I/O. So it's waiting for data to be retrieved from a file. Then P2 has to leave the CPU and go to the waiting state. Why would you leave the CPU? For it to be used by another process. Let's say P3 now is using the CPU, or P1 if that's the only one that is in the ready state. Why would P2 go for the waiting and leave the CPU again? Let's take this example. All right. You are in McDonald's waiting online, and you have here the cashier. All right, here you are. Okay, you have your brother with you or your sibling with you. There's another line here, like people waiting. All right, you're now facing the cashier. You found out that you don't have your wallet on you, so you can't pay. Basically, you have one of two options. The first option is to send that sibling home to retrieve the wallet and come back. But while this sibling is doing this trip, you're still gonna be facing the cashier. So you're gonna be facing the cashier. That's a very, very bad option. Why? Because then you're delaying everybody else. It's not that you are waiting for the sibling to bring the wallet, but everybody else is as well, which is not a wise decision. The wiser decision is that you would step aside, leave this place for everybody else, okay, to deal with the cashier, and then when your sibling is back, you're gonna take the wallet and stand in line again. Okay, this way you utilized the cashier in a better way. This is exactly what's happening here. The process, if the process is going for a waiting state, then it will step aside and leave the processor, the CPU, for other processes to get served. Now, we're doing that because the waiting state takes time. The I/O takes probably millions of times bigger than the CPU cycle. Okay, so if you're just doing CPU calculations, you need million instructions or something to be equal in time complexity to the I/O that you are doing. And that's why it has to step aside to give a chance for everybody else to be served, and then when the I/O is done, then the process will go to the ready state again, waiting for its turn to be picked up again. I hope this is clear. We're going to be continuing with the next part.